All right, so in this lesson video, we're going to be going over 3.5 inverse trig functions. Okay, so trig functions, they take an input. That input is an angle, the measurement of an angle, and they give you an output, which is the ratio. Now, depending on the trig function, that ratio is different sides of a particular right triangle, right? So when we have our angle, so we'll just draw something in quadrant 1 here. So let's sketch out an angle here in quadrant 1, just for reference's sake. And, here's the point on the unit circle that's passing through it. And we can go ahead and drop this right triangle in here. And yeah, again, depending on the trig function, the ratios are going to be slightly different, right? So this side over here is our opposite. This is the hypotenuse. This is the adjacent. The opposite is the y coordinate at our unit circle point, and the adjacent is the x coordinate, our unit circle point. And so the trig functions take this angle as an input, and then they ratio these different things. So opposite over adjacent, opposite over hypotenuse, adjacent over hypotenuse, whatever, depending on our trig function. That's the output, is that ratio. Well, every function, mathematically speaking, it's nice to have an inverse, something that does the reverse of that. And so there is where we get what are called the inverse trig functions: sine inverse, cosine inverse, tangent inverse, and so on. They take the ratio as an input, and they give us the angle back out as an output. So you can see here, this little diagram down here. Sine takes an angle, gives us a ratio. Sine inverse will take that same ratio and tell us what angle it was that goes back with it. So these things kind of undo each other, and that's really powerful, really useful. Let me go back to that actually really quick. It's really important to notice this really connects to the idea of inverse functions that we spent some good time talking about in the pre-calc first semester. Notice how the domain of our inverse is the range of our regular function, and the other one switches also. The domain of our regular trig functions is the range of our inverse. There are some small issues with this that we're going to run into that have to do with the definition of a function, but we'll touch on those in a little bit. All right, so here we have our regular trig function, y equals sine of x, y equals the sine inverse of x. So this -1 is not an exponent. It's the way that we denote inverse. You'll probably remember that, right? When we had a function, if we wanted to represent the inverse of that function, we wrote it this way: f inverse of x. That little -1 denotes inverse. It's kind of confusing, especially coming off a chapter where we were looking at things like this, where this is an exponent, but this isn't. That's a little bit confusing. I understand that, but this is just the inverse. Small thing, sometimes inverse functions are written in this way. Some people write this as arc sine and arc cosine. These are the same thing as the inverse functions and arctan. Some calculators use them, and sometimes they're written in math textbooks and stuff in this way. I think it's just to avoid this confusion with the -1, which again comes from the inverse function notation. All right. So let's go ahead and take a look at what's happening with these things on the unit circle. So if sine of pi over 6 is 1/2, so here's pi over 6, here's the angle that we're talking about, and the sine value is the y coordinate. So sine of pi over 6 is 1/2. You can see that. Then sine inverse of 1/2 equals what? We want to know what angle gives us a sine value of 1/2. Well, shouldn't it be this angle? Shouldn't it be pi over 6? Yeah, of course. That works. Isn't there somewhere else on our unit circle that has a sine value of 1/2? If we just kind of flip over here across the y-axis, you can see at this angle right there, there's another angle. 5 pi over 6 has a sine value of 1/2. So what's the answer? Is it pi over 6? Is it 5 pi over 6? Which one's correct? Is it both? It's kind of both, but we restrict it. We actually decide that this is the proper answer when we're evaluating an inverse trig function. We only look at a certain part of the unit circle, and this right here, it falls within that particular part of the unit circle that we're going to examine for sine. Now, that doesn't mean that this is totally wrong. This is important to know, and this is important to find. And when we're solving equations, we'll want to see both of these things. I like to draw the comparison to something like this. When you are taking the square root of 16, usually you only give me one answer. You say it's 4. And that's true, right? The square root as an operation has a principal root, we call it, of a positive number, and it's 4. But when we use this square root operation to, say, solve an equation like this, we do not just take the principal root. We account for both of those things, right? We take the square root of both sides, and we say, actually, x is equal to positive and negative 4. Both of those are solutions. Well, this is kind of the same idea. We said, yeah, I mean, both of these angles give us the correct sine value. But when you're just using sine inverse as an operation, you really only consider this one particular solution. But if we're going to solve an equation, we do need to make sure we understand that both of these things do have a sine ratio of 1/2. Anyway, I like to compare it to the square root because it's a very similar idea. All right, and let's take a look at this last one. What about cosine inverse of negative root 3/2? So it's, again, that's asking us what angle is going to give us a cosine ratio of this. Cosine is the x, and we can see it here. This is the first one, and here is another one. The cosine values are actually symmetrical across the y-axis, but sorry, across the x-axis here. These are both of these. So which one is the answer? Is it 5 pi over 6? Is it 7 pi over 6? Well, actually, it's this one, 5 pi over 6. Because we only look at a certain section of the unit circle for cosine inverse. But both of these answers are valid. If this was involved in solving an equation, we would want to consider both solutions. Anyway. All right, so remember the definition of a function, right? A function is a relation from a set of inputs to a set of possible outputs, where each input is related to exactly one output. So we were running into the situation where, let's actually go back to what we were talking about. We were talking about sine inverse of 1/2. And we said, okay, fine, our input is 1/2, that's our ratio, and the output was two things. It was either pi over 6 or 5 pi over 6. Well, this breaks the rules of functions, right? This says that this single input has two outputs. So we have to restrict this. We have to say, no, 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 no. We only want our input related to one output. So we have to choose which one is it. And we do this. So same reason when we did something like this, we didn't give ourselves two outputs because we wanted it to be a function. We said, no, 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 principal root only the positive number. Well, we're going to do the same thing. We're going to only look for answers in certain parts of the unit circle for sine inverse and certain parts of the unit circle for cosine inverse. They're a little bit different than each other, but we only look at certain parts of the unit circle. And therefore, we get that singular output for our input, and it allows it to be a function. So again, here's the pictures, right? The units, the sine curve and cosine curve, and we can see these are functions. But if you were to flip it, if you were to think about it in terms of its inverse, right? We run into some issues because there are an infinite number of solutions that say have a sine coordinate of 1/2. There are an infinite number of angles, right? So let's just say this is 1/2. There's one here, there's one here, there's another one over here, and keep going on. There's just an infinite number of them. So if we try to reverse that, which angle is the answer? Well, we only look for certain of those angles, and so we have to restrict it. All right, so for cosine, we restrict our range only between 0 and pi. For cosine inverse, between 0 and pi. So 0 is here, pi is here. We don't look at the bottom half of the unit circle at all for cosine inverse, just the top. For sine inverse, we only look from negative pi over 2 to pi over 2. This causes some small issues because angles that fall down here in quadrant 4 should be expressed as negative angles. So when we go here and we find an angle that matches our answer and it ends up being, I don't know, right here, and we look at it on the unit circle and we say, oh yeah, you know, that's this angle. It's can't even think of what this would be real quick, but 3 pi over 3, like 5 pi over 3, right? I think that's what the angle would be here. Well, we say no, we don't get 5 pi over 3 because that's not falling in this range between negative pi over 2 and positive pi over 2. That's a much bigger angle than pi over 2. That doesn't fall in the range. So what we do is we have to express it at this negative angle, and the negative equivalent is negative pi over 3, and that's the angle that fits in the range. So whenever we find an angle for sine inverse that ends up being in quadrant 4, we do have to do a little extra work and find this negative angle. That's the proper output because it has to fit inside of that range. We also use the same range for tangent inverse. So if we're finding tangent, we do only also look for that part of our unit circle. Okay, let's go ahead and let's just see what's going on with this. Let's actually just try it. So I'm going to do the cosine or the sine problems first. So I'm going to do, not what I meant to do. I'm going to do the sine problems first, just so that I'm looking at the same part of our unit circle. So again, for sine, we go from negative pi over 2 to pi over 2. So I'm looking at this section of my unit circle. I'm looking for the sine inverse of negative root 3 over 2. So negative, that means we're down below the axis here. And it's right here. This is the angle we're looking at. We're looking at this angle. Again, this is actually the exact example that I was just talking about in the kind of quick write up here. It's 5 pi over 3. That does not fall in the range that we're supposed to use. We are supposed to be looking between negative pi over 2 and pi over 2. Or negative 90 degrees to positive 90 degrees. That angle is 300. That falls outside of it. That's 5 pi over 3. So we would need to figure out the equivalent this direction. 60 degrees this direction, 60 degrees this direction. We're talking about a negative pi over 3 down here. Use that first quadrant up here to sort of help me. What angle equivalent is up there? It's just the negative version to go down here. So this is negative pi over 3. Let's put that back up. Yeah, negative pi over 3. All right, and then last one here, we want to know sine inverse of 0. So where do we have a sine value of 0 in this range? It's right here, 0 degrees, 0 radians. We're going to be giving our answer exclusively in radians throughout this section. Okay, let's go ahead and talk about the cosine problems here. So cosine inverse of 1. For cosine, we look for between 0 and pi. We don't have to worry about negative angles here. We're just going from 0 to pi. Whereas cosine 1, cosine is the x-coordinate. Cosine is 1 at 0. Easy. Cosine inverse of root 2 over 2. That's positive, so we're going to be on the right side here. Root 2 over 2, x value is right there. It's at pi over 4. Again, there are other places on the unit circle that have some of these values, right? There's one down here. For instance, on that last one we did, root 2 over 2, root 2 over 2. The cosine values are symmetrical across the y-axis. You know, that would have the same x-coordinate right here. Whatever this x-coordinate is, which in our case is root 2 over 2, it's going to match it here and it's going to match it here. So that's where that symmetry happens. But we only look in that certain range for our answers. So we only give the answer that falls in that range, which is pi over 4. Okay. Summary, I'm going to skip through these. We don't need to know these. Here's what we really need to know. We're not really going to be dealing with cosecant and secant and all that. When we need to, we'll change it to sine, cosine, and tangent. We'll use our reciprocal identities, our quotient identities to change it. The domain, what are the possible inputs? Well, for sine, they match the outputs of sine. They go from -1, which is the lowest possible output for sine. That's going to be the lowest possible input for sine inverse, to 1, which is the highest possible output for sine, which means it's the highest possible input for sine inverse. Pretty simple. Cosine follows the same procedure. Tangent is a little different because tangent actually gets outputs that go to infinity and go to negative infinity. We know that because of the asymptote behavior of its graph. Therefore, we can take any number in that we want. There you go. Using your calculator, we're going to be using our calculator a little bit. This is a little screenshot of Desmos. We can do the inverse trig functions. We can actually do all 6 of them if we're using the graphing calculator version of Desmos. We can do cosecant inverse, secant inverse, cotangent inverse, whatever. So we can do all of those. We're mostly going to stick to these 3 buttons, but that's okay. Make sure to pay attention, radians or degrees. For the most part, we're going to use radians almost exclusively, but you know, we may see a problem here and there that asks for degrees. So pay attention what you want it to be in. So let's go ahead and use our calculator to approximate these particular things. Feel free to pause the video and go to Desmos and see if you can make that happen. I'm going to go ahead and do it here. Oops. See if I can get back to that screen. There we go. Domino's Pizza popped up there. Anyway, we are going to do, what was it, sine inverse of 7/8. Let me just make sure that was the, yeah, sine inverse 7/8. So to make this happen, we want to bring up the keyboard thing down here and then click functions. And here we go, we got our options. So I'm going to do sine inverse 7/8. Now, the graphing calculator Desmos does default radians. So this is our answer, 1.065. We'll probably round to about 2 decimal places for accuracy. So this would round to 1.07, for instance. If we need to change it for whatever reason, right, currently in radians, if we want to change it to degrees, we click this little tool icon and change it to degrees. Now it gives us the degree equivalent up here. So this is in degrees, different measurement, same angle, but a different unit of measurement. We're going to go with radians, though, so we'll call this 1.07 as our output. Now we're going to do cosine inverse of negative 0.6. Same idea. Function cosine inverse negative 0.6. And there we go. We got 2.21. Last one is a little bit tricky. We got to know how to make sure we can type that in. Tangent inverse of √3/5. So again, function tangent inverse. I'm going to use this button down here. You can also type in SQRT for shortcut. I'm going to hit this button, √3. Now it's really important where you start typing it as a fraction. If I press divide right now, it's going to put this whole thing in the radical. So this is not the same thing as what it was asked to do. So I need to delete that. I have to use the arrow key to click out of the square root, then press the divide button. Now that radical is only in the numerator. So got to be careful there. Another thing you can do is you can actually press divide first and then just type your radical on top. But you got to make sure that that radical is only over the numerator and not over the entire thing, because those are very different. Let's just compare those 2 things. We're getting very different answers here. So here's the wrong one, right? Notice how that this angle, pretty different, negative 0.66, or sorry, 0.66 radians versus 0.33 radians. Those are different, you know, like twice the angle. So make sure you get the right one there and express it properly. Yeah. And we're going to round these mostly to 2 decimal places, and we're almost always going to use them in radians. All right. Finding the exact value. So this is something that you're going to be asked a lot. You're going to be finding the exact value. Usually that involves 2 different processes depending on the problem. Either use the unit circle to find the exact ratio that matches your angle, that matches your trig function in the right range. So for cosine inverse, it would be between 0 and pi. For sine inverse, it would be between negative pi over 2 and pi over 2. So unit circle. The other one is if this ratio is not something that appears on the unit circle, like for instance, if we have a ratio of 1/3, there's no 1/3 on our kind of standard unit circle spots, we're going to have to make a right triangle. We're going to have to use our basic SOHCAHTOA triangle, right triangle knowledge and set up a triangle that has this ratio. So we'll go through both examples here in just a moment. I'm going to start off with the easier one. So we are finding the exact value of this. But first, let's just make sense of what this is asking. So mathematically speaking, we always start on the inside of our parentheses. So we got to figure out what this is having us do. And this is saying, well, what angle has a sine ratio of negative root 2 over 2? So I'm going to get an angle here. This is going to give me some angle. And then I'm going to figure out the cosine of that angle. Easy enough. So I'm going to get an angle here, find the cosine of that angle. So my overall output is going to be some ratio of the cosine of some angle, which is a ratio. Okay. So let's first look at the first part, that inside part. So we want to know sine inverse of negative root 2 over 2. So no, we are only looking between negative pi over 2 and positive pi over 2. Only on this side of my unit circle. I don't care about this side right now. It's not in my range. Since it's negative, we know it's going to be down below the x-axis. And that's right there. So this is not the proper angle because that falls outside of our range between negative pi over 2 and pi over 2. We need to know the negative equivalent. Well, this is the same thing as a 45-degree angle or a pi over 4. We're just going in the negative direction, so it's negative pi over 4. Use that information. Use that mirror image on this quadrant to give you the angle, but it's a negative version down here. So this becomes the cosine of negative pi over 4. What is the cosine of negative pi over 4? That's just the x-coordinate here, which was the square root of 2 over 2. And there we go. That is our overall output, again, using the unit circle. Not too difficult on that one. They do get harder. All right, example 2. So same thing is going on here. We're looking for what angle is going to have this cosine ratio. Then we're going to take the cosecant of it. So I'm looking for the cosine ratio of root 3 over 2. It's cosine inverse, so I'm only looking between 0 and pi. And I don't care about this side of my unit circle at all. I'm only looking in this range. I restrict that range anytime I'm using cosine inverse. I'm restricted to this range. So root 3 over 2, here it is. Cosine gives me that. It's pi over 6. That's it. Don't have to figure out any negatives or anything. That's just what it is. And I want to know the cosecant of pi over 6. Cosecant is the reciprocal of sine. So the sine at pi over 6 is 1/2. So the reciprocal of that's going to be 2 over 1, or just 2. And there we go. Right? Reciprocal of sine, reciprocal of 1/2 is 2 over 1. So we get 2. Can be challenging, can be easy. Then we have something that's not on the unit circle. We're going to go ahead and take a look at these in part 2. I'll see you guys there.